Okay. Hi, everyone. I'm Pietro Michelucci. I wasn't actually going to show you this, but I decided to at the last minute anyway. So I was at a TechCrunch conference in Berkeley, and I was just sitting outside, and this thing ran by, and I just had this reflexive instinct to having been an iNaturalist participant for a long time, to take a photo of it and post it on iNaturalist. So I did that despite myself, and or maybe despite Carrie. And so it was very interesting to me that what came back from the AI in terms of the recommendations was first human. Okay, so I could sort of imagine that. But then the next thing on the list was a ball python. And I thought, there's just no way I can look at this picture and see a ball python. So then, I saw some humans there as well as these robotic things, and I asked the humans passing by what they thought it might be, and their responses were much more in line with what I would have expected. Different sorts of canines and quadrupedal animals. So this sort of raised a question for me, which is obviously what's going on here? Well, how does the AI see this differently than we do? And it occurred to me that there's something about legs. And they're kind of blurry legs in this picture, so you could see the AI might not see in the pixels what these appendages or these tendrils might be. But as a human, we have a functional understanding of legs. That thing couldn't be suspended in the air unless there were legs supporting it. So it's this idea about the functionality of legs and this functional knowledge of how the world works and the physics in the world that allows any human to look at this thing and say, oh, those are legs because of what they do, not exactly how they appear, but also how they appear. And so I think this is just an important consideration as we think about the differences in how AI and humans think about things. If the information isn't always in the pixels, then the AI might struggle, and that's where we need human help. Okay, so that was a sort of a diversion. Now the actual talk. So I'm going to be talking about integrating machine and human intelligence in citizen science, and I'm going to begin with a riddle. So what does biodiversity monitoring and biomedical engineering have in common? Don't answer now. We'll come back to this. So to understand our goals, I kind of like to look at the big picture. So if you believe the Bare Naked Ladies, about 14 billion years ago, there was the Big Bang. And then, of course, about 4.5 billion years ago, the Earth coalesced from space dust, except it didn't look like that. It looked more like this at the time. And then about 3 billion years ago, there's evidence to suggest that that was when there was the emergence of life. And with the emergence of life, began information processing. So why do we think so? Well, an obvious example is reproduction, complex information process, and more simply, just the ability of an organism, such as the archaic bacteria, which were among the first life forms, to respond to their environment. So they could respond to light or moisture or magnetism, and then and actually physically move in response to that. So how does this work though? So there are these biochemical processes that are sort of in some kind of cascading arrangement, but ultimately these boil down to a simple decision process, which is if you see light, rotate your flagellum this way, and if you don't see light, rotate your flagellum the other way, assuming you have a flagellum to rotate. And so this served a purpose, right? And I think that this is important, that it served a purpose. So this happened to be so useful that we evolved specialized cells to do more complex processing, obviously called neurons. And then over time, these arrangements of these cells in the cluster of brains have gotten increasingly larger. So why, right? Why? What is the survival advantage of this? And to put that more specifically, what are the adaptive benefits of increasingly sophisticated information processing capabilities? So let's consider what brains do. Brains make predictions, and when these predictions are good, we're more likely to survive. And when they're not, if we're lucky to survive, our model improves. So one way we can answer this question is to say that learning leads to improved survival-based predictions under a wider variety of circumstances, right? And so that's kind of what we're trying to do. So very recently on the cosmic timescale, we ended up with human brains, and they're arguably the most complex information processors in the known universe. And I realize I'm saying this to a room full of scientists who are aware of whales who have also very complex brains that might rival human brains. That said, the human brain has about 100 billion neurons, maybe more recently they're saying 80 billion neurons, and about a quadrillion synapses. It's a lot of information processing capability. And it operates on about 20 watts. So you can get about that speed in supercomputers, but it takes about 1,000,000 times as much power to achieve that speed of processing. So what have we done with these amazing brains? Well, we've invented things, and these inventions have helped us, but they've also led to secondary effects that we can't fix. And so now we need even better predictive models in order to tackle these new problems. So what are the information processing resources that we can tap to solve these now bigger, seemingly insurmountable problems? Well, we have the kinds we've invented. We have computing machines, but we also have life processes that we can tap. And I think we can use technology itself that we've invented to help us connect these processors together in sensible ways to enable a kind of hybrid intelligence. And if we're lucky, that hybrid intelligence might exceed individual human intelligence and lead to some potential solutions. So we could use these methods to develop increasingly faithful models of the universe, and in particular of the Earth system, so we can more easily identify solutions and understand the secondary impacts before we implement them. So human computation is like a first step toward achieving this level of integration among the different kinds of information processors we have. And in human computation, we try to leverage the complementary strengths of humans and machines to achieve what neither can do alone. So in 2014, I was looking for a problem to solve with human computation. It was like a hammer looking for a nail, and I stumbled across this nail at Cornell University. I met Chris Schaefer, who was doing Alzheimer's research, and so it's long been known that that Alzheimer's patients have about a 30% reduced brain blood flow relative to healthy people. But until recently, we didn't know why. And Chris and his team at Cornell recently discovered that in mouse models of Alzheimer's disease, this reduced blood flow is caused by capillary stalls. And they also discovered that restoring blood flow in the mice that were given the human version of Alzheimer's disease, which comes with both the cognitive symptoms and also the physiological correlates, that when they restored the blood flow in these mice, their cognitive symptoms went away. Their memories were restored even within a few hours. So this was a remarkable finding. And the special imaging techniques that they used to make these discoveries, they realized could be used to investigate treatment possibilities based on safely restoring brain blood flow in humans. So what was the problem? The problem was, as you might expect, that there was sort of an analytic bottleneck. So it would take for 1 week of imaging to collect the data, it would take 6 to 12 months just to answer a single research question, which would result in kind of a glacial pace for the research. So I asked Chris to show me. I said, "Show me what this analysis looks like. I want to understand why this is taking so long." And he showed me how they're looking at these capillary segments to try to figure out for each one, whether blood was flowing through the capillary segment or stalled, because they had to sort of count in order to assess the degree of stalling that was occurring, which also entailed keeping track of the different capillaries. And as soon as I saw it, it reminded me of a citizen science project I participated in 2006 called Stardust at Home. Maybe some of you know this one. In part because I knew they were looking through different levels of the imagery in the mouse brain, and that in the Stardust at Home project, there was sort of this similar idea of looking through layers of aerogel. So in Stardust at Home, they flew a comet through the tail of a, or they flew a satellite through the tail of a comet, and they collected particles of the comet dust in this aerogel and brought it back to Earth, and they were trying to analyze it. In their case, it was sort of a needle in a haystack problem. They anticipated there would be just a few of these tiny microscopic particles embedded in the aerogel. And so they employed crowdsourcing through this virtual microscope interface in order to crowdsource the analysis of the aerogel. They had about 1 million digitized images they had to go through. And so remembering this and seeing kind of the similarity in the analytic process, I realized that we could basically just apply this directly to the Alzheimer's data. And in fact, our proof of concept for our own citizen science platform ended up being shoehorning the Alzheimer's data into the Stardust at Home platform. We just put different branding on top, but then we knew we had something. In fact, the folks at the lab said they'd rather use this to do their in-lab analysis than their current tools. So that was encouraging. So I presented this idea right away at the National Alzheimer's Summit at NIH, and I was encouraged to pursue this by a program officer, and I went through the process to try to get some funding. And we got really strong positive reviews, but it only takes one very negative review to kind of thwart you. And we got this one review back that said, "This proposal suggests a way to harness the power of the people and the internet to speed analysis. However, the reliance on untrained individuals with various motivations renders the impact questionable." So in the proposal itself, we were proposing to actually test the validity of the crowdsourcing method. So we were kind of disappointed by this result, but in the end it was funded by Bright Focus Foundation, and we were able to proceed. So we ended up creating Stall Catchers, which is an online game that anyone can play to speed up Alzheimer's research. And when people play Stall Catchers, just like in any citizen science project, they're not themselves being studied, they're actually participating in the conduct of the research and analysis. Let's see, something got stuck here. Okay, here we go. And it turns out some people actually like playing this game. In fact, a lot of people do. Today, we have over 37,000 registered Stall Catchers players. On any given day, 50 to 100 people show up to participate and contribute to the data analysis. We're analyzing data about 5 times faster than the lab, and so we're answering research questions about once every 1 to 2 months, which is of course a lot better than every 6 months or a year. And we've had some findings that have been published, and we acknowledge whenever possible that the Stall Catchers volunteers were co-authors and part of the research team. Also, the process that the lab is going through is to try to unravel the underlying molecular mechanisms for the stalling phenomenon in order to figure out what could be a safe treatment. And where you see green check marks here, these are where the questions have been answered, or where the answers to these questions have been enabled by stall catchers, and the red question marks represent areas that are still being researched and will be answered through stall catchers analysis. And in fact, we have some promising findings that look like if humans respond the way mice do, that it could lead to potential treatment. So in terms of the human-machine collaboration that's operating in stall catchers today, obviously we use aggregation methods like a lot of projects, and I think this was covered in Zooniverse as well. So the idea is we don't trust one individual member of the crowd to give us the correct answer. We combine answers from many different people, and the number of people that it takes to tell us whether a capillary is flowing or stalled, we call it our magic number, started out at 20. So when we did our first validation study, we realized that just doing simple averaging over the responses, that it would take between 15 and 20 people to achieve with consistency 0.95 sensitivity and specificity, which was our research targets. But we felt this was very inefficient and that we could do better. But at that time, the main goal was just to say, is this feasible? Can we crowdsource this, and can we produce high quality research data? Ultimately, we improved on these methods, and we sort of track the performance characteristics of the people who are participating in the platform, and we used a kind of a weighted average approach. And also a dynamic stopping rule in order to come up with an answer more efficiently. And today, I think on average, it takes, here in this slide, I say 7, but I think today we're operating about 4.5 people per answer. So even though non-expert members of the general public may not analyze data as well as a scientist would, it turns out the crowd-based answers in stall catchers are even better than the in-lab technicians. And so funny thing happened after we ran our validation study. The Cornell lab decided to analyze a portion of that data set in the lab just as an added sort of check to make sure the crowd was doing okay. And they came back to us and they said, yeah, we have some concerns because our in-lab analysis isn't really lining up with your crowd answers. So so we kind of had this pause moment, and we went and met with them the lab, and when we looked carefully together at each instance where there was disagreement between the lab techs and the crowd, it turned out that they decided that the crowd was correct in almost every case. Oh, it looks like things kind of froze up here again. Okay, so so in the end, our goal is actually to fully automate this analysis. I like to say that from our perspective, citizen science involves planned obsolescence. There's some strange sounds in the background. I don't know what's causing that. Hopefully you can still hear me okay. So so these are the ways that we're sort of tackling the problem or the challenge of automation today. So originally there were these two analytic bottlenecks. I only mentioned the analysis of the individual capillaries, but we were also trying to figure out the location of each of these vessel segments and how they map into a broader vascular network. And so, you know, we considered adapting iWire, which, if you're familiar with it, is a platform. Sorry, is a platform that that's used to to crowdsource segmented networks of neurons. And we sent one of our colleagues to Princeton to work with Sebastian Sung, who created iWire, to learn the methods. And this was Mohammed Hafjafahari, and he came back and he was able to take those methods and actually fully automate the part that we needed. So we ended up not having to create a separate crowdsourcing platform for mapping the vasculature. That became a completely automated method. The next thing we were trying to do was to figure out if we could improve quality assurance so that we were only passing actual capillary segments to the crowd to analyze. So what you see in this image is a venule, which is much too large. It's not the kind of thing that would ever stall unless you had a serious stroke or something. And so this is not the kind of thing we'd want to pass along. In fact, there are all kinds of different flavors of bad images. And so we trained a neural network, and it turns out it was about 92% accurate. And so we use this to filter out, you know, some of the problematic images. And then finally, you know, there's this basic task, which is mostly, which is completely crowdsourced today, of classifying the flowing versus stalled vessels. And we experimented early on with some machine learning models, and we thought, well, one thing we could do is if we can build a model that can give us a confidence estimate, then we could just allow the model to kind of grab the low-hanging fruit and answer the 10% of the easiest vessels and then pass the rest to the humans. But we never ended up doing that. So so what's the problem? Why is it so hard to get machines to do this part of the classification? Well, one aspect is that if you have a machine learning algorithm, it's going to give you the same answer each time. So if you have 3 machine learning algorithms and they're all the same, it's always going to get the same ones right and the same ones wrong. And the wisdom of crowds sort of relies on the diversity of the crowd. So even if individual members of the crowd aren't as good as the machine learning algorithm, in combination, because of this diversity, we get very strong results. Let's see. So that's where we are today. More recently, we've been looking into the same question of how do we do better on this this binary classification task of flowing versus stalled. So so toward this, we created an experimentation toolkit. We've been building a data science ecosystem called Civium. And part of this involves making it easier to create citizen science projects and then run experiments on them in a sandboxed version. So this experimentation toolkit allows someone to design a study around an existing citizen science project, select the data set, invite participants, and then run experiments on it in this kind of isolated or quarantined environment, and to do it without writing any code. So we embarked on a project with Microsoft Research, and what we were trying to do is figure out if a human might do better if it's paired with an AI assistant that makes suggestions to the human, and then the human can decide whether or not to accept that suggestion. So in our initial experiment, what we're seeing is preliminary evidence that when paired with an AI assistant that's programmed with a certain kind of response, so these are simulated AI assistants, and so we program it with a certain response bias, that when that response bias is complementary to the human response bias, we actually get a synergistic effect where the human and AI working together do better than each does on its own. So this is kind of an exciting initial finding. The other thing we've been pursuing is we realized that machine learning's improved over the last 4 or 5 years, and we now have millions of human-generated examples from stall catchers that we can use to teach the machines. So we ran a machine learning challenge. And in this challenge, there were about 900 human competitors, resulted in 55 machine learning models. And so what you're seeing here is the performance characteristics in terms of sensitivity and specificity of each of these 55 machine learning models. So the vertical blue line represents sensitivity, and the vertical orange line represents specificity. And stall catchers today exceeds this green dotted line at the top. So in order for a machine learning model to do as well as stall catchers, then both the blue and the orange line would have to be higher than this green dotted line. And as you can see, none of them are. But there's still some pretty impressive looking models here. So then, the question is, a lot of work went into this. We've got some great machine learning models. Is there anything we could do with these? So one of the interesting findings was when we looked at the response bias of these different models, that the distribution of response bias was very similar to the human response bias that we saw in our stall catchers participants. And so this compelled us to look more closely at the models themselves to see, are they fundamentally, architecturally different in some way? And it turns out they are. They're different on many different dimensions. So these were the 3 winning models. And you can see both in terms of pre-processing and training, they take different approaches, and architecturally they're different, and their response strategies were also different. So it looked like there were some very fundamental differences that accounted for this diversity. So then it occurred to us, if these models truly are that different, what would happen if we let them play stall catchers, just like humans do, right? So so we thought, let's make this possible. So we invited Laura Onak, who created one of the winning models, to join our team and work with us. We created a SitSci bot API and an agent wrapper, and then we took Laura's model and we put it inside that agent wrapper, and she named her bot Gaia. And in the interest of time, I'll skip this part, but there's a nice explanation of where the name comes from. And we ran a pilot study. We took a data set that had already been analyzed in stall catchers, and we analyzed it again, but this time with Gaia participating in the crowd along with the other humans. And I don't know if you can see here, but bot Gaia is number 3 on the left here. So Gaia was actually on the leaderboard as well. And so it turns out that we did an equivalence test to compare the cohorts that included Gaia from the new study to the original data set, and we compared the human-only cohorts from the new study to the original data set, and actually the hybrid cohorts were strangely more similar to the original analysis. So this looks very promising as an approach. So both of the 2 studies I just mentioned are in the process getting written up. One of them is in press at ACM's Tochi journal.
Well, Pietro, we have 2 more minutes.
Okay, thanks for the warning. Yep. So what are we planning to do next? We want to do some more of these human AI partnership studies. I won't get into the details now, but now that we have some real models, we can start to take some of these models out of the machine learning competition and actually integrate them back into these human AI partnership studies. And then in terms of this agent-based approach, sorry about that. We're interested, of course, in seeing what happens if we have more than one SitSci bot integrated with the crowd in a given cohort. What happens if there's only one human in each cohort? Is that enough to to elevate the ensemble performance to the existing stall catchers level of performance? And of course, ultimately, what happens if we apply our wisdom of crowd methods to machine-only cohorts? So that would be quite interesting. And in the meantime, we're building out this data science ecosystem so that we can support more sophisticated methods for having simultaneous learning among the machines and the humans within the same system that also allows us to do experimentation and ultimately analyze the data much faster and with high data quality. So if you're interested in learning about this ecosystem, you can go to civium.io, which sort of describes the rationale underlying this. And in the end, we're hoping that this ecosystem might bring us a little closer to achieving this vision of an integrated information processing system that endows us with the capability to do the kind of prediction that we need to solve the wicked problems, many of which result from the technologies we've created. So just to go back to the riddle from the beginning, so what does biodiversity monitoring, such as iNaturalist, and biomedical engineering, such as stall catchers, have in common? And the answer is coronavirus. And we could talk about that later sometime. Okay, so thank you very much.
Thank you very much. I think we have time for one question. Anybody from here in the room? Yeah, we have somebody.
Hi, my name is Shlomo. I'm from Tel Aviv University. Thanks so much for the talk. As a human who's I just finished going over hundreds of thousands of images, I'm interested in what you were saying about the AI assistant with the complementary bias that helped reach higher success rates. I'm wondering if you could elaborate on that a little bit, what that AI assistant looked like compared to the ones that didn't work as well.
Yep. Thanks for the question. Great question. So these were simulated AI assistants because for the purpose of the study, of course, we wanted to understand how the performance characteristics of these assistants interacted with what we knew about the humans who were in the study. And so we had one that was heavier in terms of, so they didn't provide perfect answers. They were 75% accurate. Some of them erred on the side of false negatives, and the other erred on the side of false positives. So then, one of these assistants would look at the vessel next to the human and say, yeah, I think this is flowing. Over time, the human would observe when the simulated assistant was correct or incorrect and start to presumably come up with a model of when do I trust this assistant, when do I not trust this assistant. And we saw that in the circumstance in which in the cases where the human was most likely to be wrong, the assistant was most likely to be right, they would develop this, they would figure out when to trust the assistant, and then collaboratively, they would perform better. So, one of the things you can do with a machine learning model is you can calibrate the bias of the model. So, so we have a few things we could do with this. One is we have a collection of 50 models in our repertoire now, or 55 models. So if we want to put them into, use these in this kind of partnership approach, then we could do matchmaking where we say, oh, okay, we know from past experience that this person tends to err on the side of false negatives, and we know that this machine learning model errs on the side of false positives. Let's pair them up. And we do this kind of matchmaking, and we can see what happens.
Thank you very much. Thank you once again.
Thank you.